I continue with a few words on the other workflow management system which we provide and support in the Material Digital framework, that's Pyiron. I mainly want to do this here in terms of speaking about some examples, and I would like to indicate again, there will be the hands-on session in the afternoon from 1 to 3 p.m., which is intended really to guide you, walk through you Pyiron from really a user perspective, telling you what kind of steps need to be done. That is nothing I will cover now here, but this will be done in the afternoon. I start with an example which is one of the first we have put also in the workflow store, and you have seen it if you have been in other presentations of Material Digital before, because it's so simple. It's a typical mechanical problem. You have some membrane, you have some well-defined boundary conditions of the membrane, and you want to see how it reacts to a Gaussian load, and that's basically you have to do some finite element simulations. I don't go into the material science here, but this is a rather intuitive example. What does it mean here to have such kind of workflow environment? It basically means you have this materials problem. You have to generate your sample, that's your membrane. You have to define your boundary conditions, and then you have to solve this partial differential equation. I'm sorry for this abbreviation here, partial differential equation. And then the code gives you some output which you translate to something generic, and you can make a parameter loop over different materials parameters, collect the data, compare the data, and learn something about your materials model this way. So in Pyiron, that is basically a way of bringing your material science concepts into Python code, but in a structured way, which also allows you to concentrate on the material science, and that you don't need to care about the technicalities of how the software is started, how the data are stored, and all this. And so it means you have to here think about, for instance, the geometry of your material, perhaps some materials parameters, as well as your boundary conditions, say Dirichlet boundary conditions, some parameters, some constants you need, and then you execute the corresponding workflow to solve the Poisson equation, for instance, and you get a nice result. That's still more or less Python code, as I said, in a way simplified that you don't need to take care of technical aspects. To really think about a workflow and this interoperability of workflows, we have transformed these kind of active workflow descriptions into a function-based approach. That means we define different steps which need to be done, like the solving of the Poisson equation, as Python functions, and then you have decorators, and this makes you a node which you can then combine with other nodes, and so several nodes together make a workflow. Yeah, you have a workflow which is called Poisson membrane, and then you have some steps like you define your boundary conditions, you define your load, and then if you combine these steps, you have a workflow. You can visualize this workflow automatically with this draw command, for instance, and then you have the different functions. Here indicated as different boxes. Each box stands for a function, and these are connected. And that gives you the flexibility of now adding and defining nodes and macros. It gives you the chance to do some semantic annotation. There are other features. Actually, I should have removed this plant here. That's meanwhile available. Also to hash the inputs and outputs in order to reuse also then the nodes. And then also the plan is to distribute these nodes for others. You can, as I said, start from the Python side and then have a graphical representation. We can also do it the other way around. We have a graphical user interface. For instance, we have here the node library for this Phoenix problem. You can select the relevant nodes, put this on this kind of board here on the right-hand side, and in this way combine different steps to a workflow. So you select the desired node. Let's say zoom in. You can change parameters by hand, or you can take over parameters from a previous step, and you can do this also in a semantically correct manner. And in this way, you get then, when you press the run command, your profile of this deformation of your membrane, for instance. Yeah, so you can do both. You can always run, but you can also look at the source code of underlying Python code. Maybe at this point, let us make clear again. So I've spoken here about Python code and about workflow management. What is the difference? What is the advantage of using this kind of function-based workflow style? So we often hear comments like, I already have my code in Python. That's nice, because then it's very easy to make this transformation. I also heard this comment, anyway, Python already delivers results I want, so why do I care about workflows? I hope with all the motivation at the beginning, this became already a bit clear, but maybe to comment a bit really from the more technical side, and this will be deepened later in the afternoon. If you just take Python code as it's here, and then you have some get elastic constants, then we have no semantic meaning for these parameters which are here used as inputs for the function. Also, the underlying directory structure might be unorientable. Then you see here a list of elements. Aluminum is mentioned twice. The computer code doesn't know this, doesn't care about this, but he would like to retrieve previous results. You would, that's what I mentioned, like to automate things like submission things to a computer cluster. That's something you don't want to take care of. But also look at this here. Get elastic constant, maybe do different things, but the intermediate results get lost when you just hand it over to elasticity. And also the provenance of elasticity once it enters into this function here is not clear anymore. So these are some advantages where structured workflow management system, which also handles the semantics of the workflow, is useful. The last point is the more general point, which Jörg already mentioned. We have often the challenge with these kind of Python codes that once the author departs, or even if the author himself doesn't look at his own code for a few months, then both the workflow as well as the results become often unusable, because they are not done in a structured way. Another example in Pyiron to show this kind of performance functionality of Pyiron a bit would be, I would like to calculate a phase diagram. That's here magnesium calcium. That's one of our projects. So you would like to know phase diagram means under which chemical composition, your calcium content, at which temperature is this kind of intermetallic phase stable, for instance. That means you need to calculate at the end free energies of different phases. And this cannot be done by a single tool. You do have to combine different software tools to do this. Yeah? So coming back to my picture, you need a framework of different software tools. Yes, that's something we have. For this purpose, for the workflow which we want to do in order to get them to the phase diagram, it's not only one code here, that you need these different codes. And the codes are, you need to have some high quality data, which you get from density functional theory. You would, however, in order to make then high throughput thermodynamic study, transfer the knowledge from density functional field theory into what we call machine learning interacting potentials, or machine learned interacting potentials. That's a way of getting the interaction of atoms much more efficiently described based on machine learning models. And then there are tools having this machine learning potentials available to calculate thermodynamic properties, free energies or Gibbs energies, and to combine them to phase diagrams. So that would be yet another tool. So we have 3 different software tools which we want to put together, and that's done in Pyiron. And again, that's an example which you can look at the QR code here and play with it yourself with this demonstrator, or you join the session this afternoon. There will be at least quickly also mentioned, even though it's not the main example this afternoon. It shows here again what is behind this. Sorry for this kind of very full slide, but it's only putting into pictures of things I've said already. So we combine data generation with ab initio density functional theory, and we have tools for this. No further details. VASP is a software tool. Assist is our tool to generate structures. SQS is an abbreviation for special quasi-random structures that is doing this random distribution of atoms. Don't care about these details. Then we need these machine learning models for describing the interaction of atoms. And again, there are a few abbreviations here which just stand for different concepts of machine learning models. For instance, ACE stands for atomic cluster expansion. Okay, then we have a machine learning model. Then we need to validate it. We calculate certain properties like bulk modulus or the convex hull or the phonon spectrum, use this validation to make an active learning in order to improve our data set, to come to better potentials. And once we are satisfied, then we can use it to calculate phase diagrams. Again, that's something which is a complex workflow. I don't want to go into all the details. Just show you, if you join this afternoon, then you will see this kind of screen. You will be able to play with this kind of interface. So it's again starting in a Jupyter environment, but you start your graphical user interface. That means you get access to the node library. You combine the nodes which are necessary to, for instance, calculate such a phase diagram. If I just take the last step of the 4 I've shown before, you can always look at the source code of the underlying nodes of the calculation steps in Python, and you can always switch back between Python and the graphical representation, staying within the Jupyter notebook environment. And then you can run it, press the run button, and you get your phase diagram, for instance, for magnesium calcium. Based on machine learning techniques, so with all the most modern tools available, you can perform your calculations without that you need to be an expert how to actually train such a machine learning model, because the underlying workflow is provided here. Of course, there's always a danger. This was this caveat which Jörg mentioned earlier. If you have no idea altogether what's going on, then it's dangerous to work with the results. But if you have understood the underlying concepts but don't want to take care of all the software technicalities, then that's the right way to go.